In this video, we're going to talk about phase diagrams. They're kind of like it's the 3D version or 2D version of a heating and cooling curve. A heating and cooling curve has a lot of information for a specific pressure. Like it's giving you the temperatures of phase transitions as you input more heat and change the temperature, but it's all at usually 1 atmosphere, so like sea level or 760 torr or 760 millimeters of mercury. So phase diagrams are actually going to plot phase transitions, not just versus temperature, but also with pressure. And so we get these diagrams that look like the one you see on this slide. And this is for water, it's phase diagram. As we see that the boiling point or the melting point of a compound or the sublimation point changes with pressure. And that's represented here. And so we can see that at lower pressures, we don't even form a liquid. That's when we just see sublimation. At higher temperatures, we see all of our compound go from solid to liquid to gas first. And so on this, as you navigate it, all of these lines that I'm about to highlight, these are all phase transitions, right? So those places where the temperature would stay constant while you were applying heat. And so we have our sublimation curve. So that's really going to be as a solid goes to a gas or a gas goes directly to a solid without being a liquid. We have our fusion curve. This is really melting, right? So this is a solid going to a liquid. And we have then also our vaporization curve, which is our liquid becoming a gas. And so these will give us an idea of the temperature at a given pressure. So if we want to actually look at a lower pressure, we could say, oh, well, we only have a sublimation curve, like a sublimation phase change. If we look at a higher one, we would see that our melting point would be a little bit different than at room temperature. And then we would have a very different boiling point because we would actually go into a different phase. Some other points that we see on here are the triple point and the critical point. So the triple point is this fantastic place at a specific pressure and temperature. So it'd be somewhere a little bit above 0 degrees Celsius and well below atmospheric pressure. We actually see all three phases exist at the same time in a phase change. So you see a solid, a liquid, and a gas. So imagine boiling ice water, right? If you can imagine boiling ice water, then you can imagine the triple point for water. It's pretty cool. I will link a video demonstration of the triple point of not water, but a different compound. So you can see the weirdness of seeing solid, liquid, and gas all in the same flask at the exact same time for something. And so then we have what that triple point kind of is the center of is the different phases, right? So whenever you navigate these diagrams, you always have your solid phase on the furthest to the left. And then our gas phase is kind of the bottom and right of our curve. And our liquid is in between those two in the upper parts. And so typically you don't see the liquid at the very low pressures. Instead, at low pressures, you usually just see solid to gas transitions instead. Now, this other point that's super interesting is right here, and it's called the critical point. Now, the critical point is a point beyond which we don't really have a gas or a liquid anymore. So it's at temperatures above a specific temperature, and this is dependent on the compound, and above a specific pressure. You'll have supercritical fluid, which is a combination of both a liquid and a gas. It has properties of both phases without being either phase at all. And so in this region right here, I'll highlight it, we have a supercritical fluid. Let's look at that again, a little bit more detail. So I really like this picture that I'm about to show that shows the two phases. And then as we increase temperature and pressure, so here we have a gas and we have a liquid, and you can kind of see that line that separates them right there, where it's a gas above and a liquid below. This is like a little window into a pressurized vessel. And then as that pressure increases and temperature increases, it changes. So we increase the temperature, the pressure increases with that since it's a closed system. And then we get something where you can't You can't see two different states anymore. And that's our supercritical fluid. And it's just one physical state. It's our fourth physical state: solid, liquid, gas, and supercritical fluid. And so this is amazing to work with on an industrial level. Think about it. It acts as a solvent just like a liquid would, right? But when you bring it down to room temperature and pressure and you open up your closed system, your solvent just evaporates. It's a gas. And so it just goes away and it leaves the compounds you were working with behind without that solvent around, which means you don't have to go through the tedious process of separating the thing you were trying to make industrially from the solvent you had to make it in. And so it can save a lot of steps in the process of synthesizing something. And so it's popular. One of the really common supercritical fluids that's used synthetically on an industrial scale is carbon dioxide. So it makes a great supercritical fluid. It's a non-polar solvent. It's fantastic. So it can do a great job of extracting non-polar compounds like oils. So it's used for things like essential oils and oil-soluble vitamins and unsaturated fats. And before, when I would teach this class, I would dance around this, but now I can do this in Washington. This is how we extract out THC and CBD from marijuana. And you can do these CO2 extractions, and they're using supercritical fluid to do it, and then it evaporates off, and you have a really nice, clean product. Or extracting lavender, whatever. So let's look at navigating a phase diagram. And this is an example of one that is not water. So I still have my solid, my liquid, and my gas, and some, depending on who generated, we'll call them vapor instead of gas. Kind of cool. I also have my triple point and I have my critical point. And what I'd like to look at here is how to really navigate this and what information you can get from it. So here I have a point on my diagram, and let's say this is the temperature and pressure I'm at, and I have a liquid sample. If I need to convert that into a gas, if I need it to undergo a phase transition, I actually have two options. Now, typically we think of, okay, well, you just heat it. And if I heat it, then I can figure out from this diagram the change in temperature that I need along that x-axis to be able to convert this from a liquid to a gas. But I can also look at what change would I need to make if I couldn't change my temperature, but I could change my pressure. And that's coming down here. So I can still undergo that same phase transition from a liquid to a gas just by changing the pressure and dropping it. And I can calculate from this phase diagram and measure exactly what is that pressure change that I need to force upon the system to convert all of this liquid into a gas phase. So let's look at a quick comparison between water's phase diagram and just about all other phase diagrams. Water is super special. So something that's really interesting about the water phase diagram is that it has a negative slope on this fusion phase change line. Now, comparing it to like all other ones, usually this line right here has a positive slope, but water's has a slightly negative slope. It's really different. So what that really means is that as you increase your pressure for your water sample, the temperature at which solid water melts or liquid freezes gets smaller. So as your pressure increases, the temperature decreases for that phase change. Now, for all other compounds, as that pressure increases, the temperature increases as well for that phase change. And that's the really big difference here between between water and, in this case, ethanol, but anything else. So why is that? Well, a lot of this has to do with intermolecular forces, right? It's part of our theme. And really the density of water. So water is really unique in that the density of its solid is less than the density of its liquid. So this means that at higher pressure for water, it's going to prefer to be in the denser state. It's going to prefer to be a liquid. And that's because the density of our liquid is greater than the density of our solid for water. And now for all other compounds that you're going to see at higher pressure, it's going to favor the solid, because the density of the solid is greater than the density of the liquid, as we would expect, right? And so water is kind of magical in this way. And I mean, water is magical in a lot of ways. So here's that structure again that we showed earlier of it in the solid state, where it's forming these 4 different interactions with other molecules, creating this tetrahedral shape. And so it's this highly ordered but spaced out solid structure compared to the liquid. And so this can go along in our laundry list of things that make water different and magical and amazing and mind-boggling, even though it's not magical. It has this low molecular mass that makes it able, like you would expect it to be a gas because it's so light, but it's actually a liquid at room temperature because of these strong intermolecular forces. Then, because of these strong intermolecular forces, it creates this tetrahedral hydrogen bonding network that forces that solid to actually take up more space than a liquid, and it's less dense, giving us this weird phase diagram compared to all other compounds. It also has an extremely high specific heat for such a small molecule, which means it takes a lot of energy to increase the temperature of water by a degree. Again, this is because it has such strong hydrogen bonding that works within its liquid and solid phases. And so really at the end of the day, strong intermolecular forces are kind of the reason behind all of these crazy things we see. It's what gives it its high boiling point, its high specific heat, its density as a solid that's so low. It's pretty interesting. Our next problem is going to be a practice problem, and I'll go through the solutions in the next video.